All right, we are back with 3.1, day 2. So let's take a look at it. So we're starting with the first subsection, how well the line fits the data, the role of S and R squared in regression. So we talked about in 3.1 R being the correlation coefficient, and if something's a linear model, then we use R to determine how well that linear model is. All right, but it's important to remember that you must have a linear model first. So here we're going to look at S and R squared. So to assess how well the line fits all the data, we need to consider the residuals for each observation, not just one. Using the residuals, we can estimate the typical prediction error when using the least squared regression line. So what does that mean? Basically, in this case, the standard deviation of residuals, or S, measures the size of a typical residual. That is, S measures the typical distance between the actual Y value and the predicted Y value. And this kind of goes back to our earlier definition of what a standard deviation is. And the standard deviation is always the typical distance something varies. So here it's the typical distance a residual varies, or the typical distance your actual value is from the predicted value of that line. So the standard deviations of the residuals S give us well, actually, I think you won't really have to worry about this formula too much, but it is Y. So your actual minus your estimated or your predicted squared, add all those up, divide by the square root of n, or sorry, divide by n minus 2, and then take the square root of that. You won't have to worry too much about that formula. But it is, your calculator will do it for you. Yeah. And it is on the formula sheet on the second page at the bottom. So I was just checking to make sure it was on there, so you don't have to have it memorized, but just so you know what it is. And your calculator will do it for you as well. So the standard deviation of the residuals S gives us a numerical estimate of the average size of our predicted errors. There is another numerical quantity that tells you how well the least squares regression line predicts values of the response Y. So the important part is of the response Y. And that is called our R squared, or the coefficient of determination, R squared, measures the percent reduction in the sum of squared residuals when using the least squares regression line to make predictions, rather than the mean of the value. So in other words, R squared measures the percent of the variability in the response variable that is accounted for by the least squared regression line. Now, I know that sounds like a lot of words. So let's take a look at what this actually kind of means. R squared tells you how much better the least squares regression line does at predicting the values of Y than simply guessing the mean value of Y for each value in the data set. And you're like, why is that coming up? I think this snippet from the textbook is really useful. So the question says, suppose we want to predict the price of a particular used F Ford 150, but we didn't know how many miles it had been driven. So we don't know our X, so I can't plug X in. So the best guess is just the mean value, right? Whatever the average value is going to be probably our best guess, right? If you didn't know how much it's going to cost, let's just find the average and go from there. But of course, this prediction is not very good because the price varies quite a bit from one change in a mile. So depending on how many miles it has is really going to influence this. So if we knew how many miles the truck had been driven, we could use the least squares regression line to make a better prediction. And how much better the prediction that use the So this last part is kind of the definition of R squared now, or more of a contextual one. How much better the prediction that the least squared regression line is rather than the average price is R squared. So R squared is how much better the um, the estimate is than the mean. Okay, so that's kind of where this comes from. And yeah, so let's try and interpret S and R squared, and we'll kind of go from there. So from a random sample of 16 Ford F-150s, we have this least squares regression equation, which is price or price hat. So is equal to 38,257 minus 0.1629 times the miles driven, or times our X value. So, and they tell us that S and R squared. And I believe if I did stat calc, I'm going to table down to A plus B to BX, it gives me ABR squared, which is 0.66. Let's see if we can get our S out of here. I think our S is in 2 var stat. Hmm. Oh, wait, hold up. To find our S, this is a standard deviation of the residuals. So luckily I have my residuals still in there. So I can go over to calc 1 var stat, but of my residuals, L3, press enter. I'm not getting my S that I want. All right, I'll explore more how to get our S, but our R squared does come from that least squared regression line. So let's just interpret our S and our R squared for right now. So to interpret S, remember S is the standard deviation of the residuals. So the actual price of a Ford F-150 is typically about $5,740 away from the price predicted by the least squared regression line with X equals miles driven. So the S is it's how much a typical data varies, and especially it's the residual, so it's how much the predicted value varies from the actual value. To interpret R squared, so R squared is 0.66, and now it'll always be a percentage between 0 and 100 for R squared. So about 66% of the variability in the price of Ford F-150 is accounted for by the least squares regression line with X equals miles driven. Now, I would kind of keep these two as kind of our templates, right? We're always going to kind of respond by this. About blank percent of the variability in the blank is accounted for by the least squares regression line with blank. So it's just the percent and then our kind of our Y and our X value, or our response variable and our explanatory variable. So normally when you do some type of regression, you're going to get the slope, which is our B value, our Y-intercept, our A value, the values of S, and the value of R squared. The question is just how do you find it? So I think S and R squared are probably the two easiest to find because they'll typically be S and R dash squared, or it might actually say R squared. We'll see a couple different variables of this. The hard part is remembering the slope and the y-intercept. So the nice thing is the y-intercept is a constant, right? It's the a plus bx, it's the a, there's no variable on it. So often the constant will be for y-intercept. The miles driven is that x value. So the miles driven is our x variable. So this is our slope. So it kind of gets tied in with the variable. This gets tied into the constant. Here's another example, and see how it says r squared. So that's how I know this is r squared. This one is a little bit harder to see the standard deviation, but it says root mean square error. So that's the square root of the mean of the squared error, and the error is how far the actual is off, or the predicted is off by the actual. That's an error, or in this case, we just call it our residual. So it's just another name for it. Again, you see intercept for a y-intercept instead of constant, and then miles driven. That's our x value. So that's why it goes with our slope. So calculating the regression equation from summary statistics. Using technology is often the most convenient way to find the equation of a least squared regression line. It is also possible to calculate the equation of the least squared regression line using only the means and standard deviation of the two variables and their correlation. So how do you find it? So you can actually find this by hand, and these formulas are on the formula sheet if you ever needed it. Except for the slope B is equal to our R, which is our correlation coefficient, times the standard deviation of Y over standard deviation of X. And that formula is exactly how this is on the formula sheet. And then y-intercept A equals y bar minus A times X, times A equals y bar minus B times X bar. And remember, y bar and X bar are the means of those variables accordingly. That formula is on the formula sheet. It's just rewritten slightly different. It's rewritten as y bar equals A plus B times X bar. So this term is just added over, but it's the same idea. You can find your A and your B from the formula sheet. So here we have a scatter plot with a bunch of lines on it. So the scatter plot shows the height versus foot length and the regression equation. So it's just another kind of data point or a data set. And we've added more lines to the graphic context. So you see, here's your X bar, here's your X bar plus S sub X. Here is your Y and your Y bar S sub X. So you could see that the difference between well, we'll just take a second. For an increase of 1 standard deviation in the value of the exploratory variable x, so as you see, I start from my mean, I go up 1 S sub x. The question is, how far in the y direction do I go? The least squares regression line predicts an increase of r standard deviations in the response variable. And this is called regression to the mean because the values of y regress to their mean. As you can see, right, this value, it's not mean y plus standard deviation of y. It's starting to come closer to that mean of y. So it's regressing towards that mean of y. So correlation and regression wisdom is this next subtopic. So correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, you should be aware of their limitations. So correlation and regression lines describe only linear relationships. Right, so here's a bunch of data sets. You could see some are linear, some are not, but they all have the exact same correlation. They all have the exact same R value. So because of that, we need to make sure that, hey, this is a linear relationship. Then I can go use an R or a correlation to describe it. So there's 3 important kind of vocab words. Points with high leverage in regression have much larger or much smaller values than any other point in the data set. So basically, let's look at. So this value here, well, no. We'll say this point here is a high leverage point because it is much larger than the x or than the x values that we had before. An outlier in regression is a point that doesn't follow the pattern of the data. and has a large residual. Basically, if it's a very, very large residual. So looking back at these values, this point right here is going to be an outlier because it has a very large residual. It's not very far away from all the other data. It just has a very large residual, so it's going to be an outlier. And then lastly, an influential point in regression is any point that, if removed, substantially changes the slope y-intercept correlation coefficient of determination or standard deviation of the residual. So for example, this graph, if I took this point away, the regression will look very different. So that is an influential point. Okay, that's an outlier. And just because it's an influential point doesn't mean it's an outlier, because it's also a high leverage point, right? It is substantially farther than all the other data points. So it does fall in a high leverage point. This point is just a straight up outlier because it has a very large residual. So the other important thing to remember is that correlation and least squares regression lines are not resistant, right? One value could substantially change everything. Right? So they are not resistant, just like means are not resistant. If you were looking at salaries and then someone made $1 billion and everyone else made 60,000, that point is really going to emphasize and pull up that mean. Same thing here. One point has the potential to really change what we're looking at. So the point for 18 here, child 18, is a high leverage because x is it's very far from the other x's, right? It's like 20 more than everybody else. So it's very far away from it. But the point 19 is an outlier because it falls outside this pattern. And look how large this residual is. It's a very large residual. 18 doesn't have a super large residual, so it's not an outlier, but 19 does have a very large residual. And you see that even here in the residual plot. Look how child 19 has a residual of 30. Child 18 doesn't even have, it's less than 10. So you could see these are different regression lines. So green is what it was, just normal. The red is without child 19, and the blue is without child 18. So you can see right now, if you took away child 18, this blue line, it changes substantially what the regression is. Now, 19 is still far. Look how the residual is still very far from 19. So 19 is still an outlier. Just because it changes the graph or the line doesn't mean 18 is an outlier. It just means it's an influential point. It's a high leverage point and it's an influential point because it influenced this line quite a bit. 19, on the other hand, if you took that away, the red and the green line look very, very similar. So 19 is not an influential point, but it is an outlier because it has such a large residual. And this is all stuff that I was kind of talking about as we went through. So another thing to remember of limitations, association does not imply causation. We should be super familiar with that. When we study the relationship between two variables, we often hope to show that changes in the exploratory variable cause changes in the response variable. But we cannot say that, and even a strong association between two variables is not enough to draw conclusions about cause and effect. It has to be an experiment. Okay, so yeah, just be aware of that. It does not mean that it causes anything. It just says that there's a strong association. All right. And that is it for today. So this first page is probably what you could have done in 3.1 or 3.2 day one. These are the learning targets you should be able to do. Interpret the standard deviation of the residuals and R squared, and use these values to assess how well a least squares regression line models the relationship between the two variables, and describe how the least squares regression line, standard deviation of a residual, and R squared are influenced by unusual points. Find the slope and y-intercept of the least squares regression line from the means and standard deviation of x and y and their correlation.